In today's video, we are going to be looking at what it means for a function to be increasing or decreasing. We will review the definition of increasing, decreasing. Then we will look at how we can determine intervals on where a function is increasing and decreasing. This is done making use of the first derivative of the function. We will conclude by looking at what is meant by extrema of a function and how to find said extrema. First, the definitions. The first definition is for increasing. Say function f is increasing on an interval. Let's call that interval AB. If for every two numbers, let's call them x1 and x2, within this interval, f of x1 is less than f of x2 whenever x1 is less than x2. In other words, as we move from left to right, xy, right? So here's x, here's y. As we move from left to right, the y value is getting larger. So we say this is x1 here, this is x2, this would be f of x1, and this up here would be f of x2. Second definition is for decreasing. And it's almost the same wording. A function f is decreasing on an interval again. Let's call that interval AB. If for every two numbers, we will again call those two numbers x1 and x2. Within that interval, f of x1 is greater than f of x2 whenever x1 is less than x2. Right, so again, if we move left to right along the x-axis, the y values are getting smaller. Here's x1, here's x2. Right, this up here would be f of x1, and this down here would be f of x2. If we are given a function f of x, recall that f prime of a denoted a rate of change at a, specifically the rate of change of f at x equals a. If this rate of change is a positive value, that would mean that the function is getting larger. If it's a negative value, the function is getting smaller. So it seems to make sense to say if f prime is positive, then the function is increasing. If f prime is negative, then the function is decreasing. And we can actually visualize this. If we take a look at a graph, let's draw a real simple one, increasing there, decreasing, and there, that's good enough. Let's draw an imaginary line right here. Right, we know that to the left of that line, the function would be increasing. To the right of that line, the function is decreasing. If we take a look at the tangent lines, right, there's a tangent line that has a positive slope. Here's a tangent line. It again has a positive slope, right? And in fact, no matter where you draw your tangent line on this left-hand side, the slope is positive. Since slope of a tangent line is just the derivative is positive. If we look on the left-hand side, let's say here's a tangent line, we can see that this slope is negative. Here's a tangent line here, let's say, right? That slope is also negative. And again, no matter where you draw it, you have negative slope. So the derivative is negative. Right at this point where the slope changes, we have a slope that is equal to 0, meaning that the function is a constant. This is a graphical confirmation of this theorem. The theorem has two parts to it. If f prime of x is greater than 0 for every value of x in an interval a to b, then f is increasing on that interval. And number two, if f prime of x is less than 0 for every value of x in an interval AB, then f is decreasing on that interval. When a function is switching from increasing to decreasing or vice versa, that means that the first derivative is switching from positive to negative or vice versa. In other words, the derivative is switching sign. The only way this is possible is if at that point where it's switching, it's 0, or the derivative does not exist. Such a point is of importance. We call such a point a critical point, or a critical number. Critical number of a function is any number, let's say x, in the domain of f, such that f prime of x is equal to 0, or f prime of x does not exist. We will now look at what is meant by relative extrema. There are two of them. First definition. A function f has a relative maximum at x equals c if there exists an open interval call it AB, that contains C such that f prime of x is less than or equal, I'm sorry, not f prime, f of x is less than or equal to f of c for every value x in that interval. Right. If we take a look, let's just look at this function right here. This point right up here would be a relative maximum, right? Because what we can do is we can essentially draw an interval any size we want, as large or as small, in which it is the largest value. That is what is meant by relative maximum. Well, the second definition then is for relative minimum. A function f has a relative minimum at x equals c if there exists an open interval, again, call it AB, containing C, learn how to spell, containing C, such that f of x is greater than or equal to f of c for all values x in the interval. Right, so if we look now instead at this function, this point right here would be a relative min, because no matter how we draw the interval, again, no matter how small or how large, that would be the smallest value. Considering examples now. First, let's consider the function f of x equals x cubed minus 3x squared minus 24x plus 32, and we wish to determine the intervals on which this function is increasing and the intervals on which it is decreasing. Well, the first thing we're going to need to do is need to determine points where it switches. That is, where is f prime equal to 0? First step is to find the critical numbers. F prime is 3x squared minus 6x minus 24. Can factor out a 3. Set that equal to 0 and solve. Right, we don't have to worry about any points where the derivative is not defined, because this derivative is defined everywhere. It's a polynomial. This would mean that x squared minus 2x minus 8 is equal to 0. This can be factored into x plus 2 and x minus 4. So we have as our critical numbers negative 2 and 4. Now to determine intervals, let's create a table. We set up an interval, and we want the sign of f prime. Now what we do is we split up the domain of f at the critical numbers. Well, the domain is all real numbers, So the first interval to test is negative infinity to negative 2. Then we'll test negative 2 to 4. Then we'll test 4 to infinity. To determine the sign in each interval, all we do is pick any number within the interval, plug it into f prime, and see what we get. Well, in this interval, let's take negative 3. This will be negative. This will be negative. We're going to have a negative times a negative. That sign is positive. Now again, the value of f prime doesn't matter, just the sign of f prime. Negative 2 to 4 has the easiest number, 0. It'll be positive times negative. 4 to infinity, let's pick 5. So it'll be positive times positive. Now we just have to interpret these results, and we say that it is increasing whenever the first derivative is positive. So it's increasing over negative infinity to negative 2 and 4 to infinity. It is decreasing whenever f prime is negative, so decreasing over negative 2 to 4. All right. Next function we want to consider now, f of x equals x to the 2/3. F prime of x is 2/3 x to the minus 1/3, or 2 over 3x to the 1/3. Now, f prime of x does not exist when x is 0, right? Because that'll give us a 0 in the denominator, and we can't have that. Also notice that f prime of x will never equal 0. So we only have one critical number. That's at 0. The domain of f was all real numbers, so that's going to be split at 0. So we go negative infinity to 0, and then 0 to infinity. This interval will be negative. 0 to infinity is positive. So f of x is increasing over 0 to infinity. It is decreasing over negative infinity to 0. One more function to look at, and that is the function f of x equals x plus 1 over x. F prime of x is 1 minus 1 over x squared, which is x squared minus 1 over x squared. Now notice that f prime of 0 does not exist. However, 0 is not in the domain of f. So it's not a critical number. F prime equaling 0. This means that x squared minus 1 is 0, and it's simple enough to see that means that x is plus or minus 1. Now, the domain of f was everything except for 0. First interval then be negative infinity to negative 1, negative 1 to 0, 0 to 1, and then finally 1 to infinity. Again, remember we're splitting the domain of f up at the critical numbers. Testing the sign. If we pick any number from negative infinity to -1, plug it into the derivative, this will be negative. I'm sorry, this will be positive. Then -1 to 0 will be negative. Since the x's are squared, changing the sign of the value we plug in isn't going to change anything. So 0 will be negative, 1 to infinity will be positive. So we have increasing over minus infinity to -1, and then again 1 to infinity, and decreasing over -1 to 0, and 0 to 1. Let's now take a look at a simple application. Here we have a profit function for a certain company. P is measured in dollars. X is number of loudspeaker systems produced. We are tasked to determine when the profit is increasing and when it is decreasing. Right, well, again, the first thing we want is P prime. Right? We want to find all the critical numbers. So negative 0.04x plus 300. That is defined everywhere. So set it equal to 0 and solve. And we should get that x is 7,500. Now the domain of profit just has to be non-negative. Right? Remember, x is units produced. So this time it's not f prime, it's the sign of p prime. So we'll go 0 to 7,500, and then 7,500 to, theoretically, an infinite number of units. Pick any number from 0 to 7,500. 1 would probably be the easiest. You'll see positive. Now pick any number larger than 7,500. 10,000 would probably be the easiest, and you'd see that that is negative. So this means that profit increases when less than 7,500 speakers are produced, and decreases when more than 7,500 speakers are produced. Let's now close up with two examples looking at extrema. The first is for the function x cubed minus 3x squared minus 24x plus 32. This is a function we already did. That is up here, right? No need to reinvent the wheel. I'm just going to reuse that chart. Interval sine of f prime. We had negative infinity to -2, -2 to 4, and 4 to infinity. Then it was positive, negative, positive. Remember, relative maximum occurs when the derivative switches from positive to negative. It's a min when it switches from negative to positive. So we have a relative max at -2. So plug in -2 into the function and you'll get 60. So the relative maximum is 60. The relative minimum occurs at 4. And so the relative minimum is f of 4, which is -48. Last one. Relative extrema of the function x plus 1 over x. Now again, this is a function we already looked at. So there's no need to reinvent the wheel. I'm just going to use the exact same chart. We have the intervals -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. And if you remember, we had positive, negative, negative, positive. So the relative maximum occurs at -1 and has a value f of -1, which is -2. Relative minimum occurs at 1, and the minimum is f of 1, which equals 2. Now, this is not a contradiction. If we were to look at the graph of this function, it would look something like this. This point here is our relative maximum. This point here was the relative minimum, right? This does not contradict the fact that the max is smaller than the min is not a contradiction because we're dealing with relatives. Right? This actually winds up, I didn't draw this exactly correctly. It's more something like this. Right? And then something like that. Okay. And that concludes this video on increasing, decreasing functions. In the next video in this series, we will be examining concavity as well as the second derivative test for determining relative extrema. I will see everyone in the next video.